Hi there, this is Mara Sangiovanni from Federico II University of Naples. I would like to share with you our new algorithm. Many of you already know that datasets for the training of large machine learning models are constantly increasing in size and complexity. Although the underlying idea is that the more the data, the better, the presence of irrelevant, redundant, or noisy elements may hamper the training process. So we developed an instance selection method that relies on Shannon's entropy concept of information to derive the notion of representativeness and redundancy of the data. The main idea is to cluster together elements sharing a similar information content and then extracting from those clusters only the most relevant instances. However, entropy calculation is computationally demanding and unfeasible on large dataset with thousands of instances. So we use an iterative split and merge approach in which we split big dataset into smaller parts. On each of those parts, the entropy-based clustering is applied, and then we move from local solution towards a global solution by merging again together clusters that are nearby in the feature space. So the dataset is projected initially into a numerical feature space, and this is an important step for data such as images. Then an initial partitioning based on k-means takes place to split the initial dataset into smaller portion. On each of those portions, the split and merge process begin. That is based on the calculation of the xi function. The xi function is obtained as the difference between the entropy of the whole dataset and the entropy of the dataset from which each point is removed in turn. The typical shape of this function is used to create a new cluster. Whenever a spike in the function is detected, then a new cluster is created. Whereas for elements that give rise to this kind of descending pattern, these elements are added to existing clusters. When the split is performed on all the portion of the initial dataset, then the k-nearest neighborhood merging takes place, in which we merge together clusters that are nearby in the feature space. This iterative process is repeated until the max number of iteration is reached, or the process converges, and we use as a convergence measure the intersection over union, since it is both computationally feasible and reliable. Then a final aggregation step is performed to merge together clusters that might have been separated due to their size. And then we have to choose a representative element in each cluster. To this aim, we use convex hull analysis. A convex hull is the smallest possible polyhedron, including all the points in the dataset, and we select as most relevant instances the vertices that are most connected, with the idea that the points that are on the frontier are the one harboring the largest part of diversity and are the most informative. We test our algorithm on synthetic data to understand its performances when the number of clusters, the number of points per cluster, and the vector length changes. But we tested it also against other state-of-the-art instance selection methodologies, using medical images as input and on different tasks and on different architectures. And the algorithm proved to be both useful and reliable, since it performs better or equal than the other methods on all the tests and in all the conditions. So we may say that it is a general purpose algorithm. And moreover, it has an unsupervised approach. It does not need labeled data, is data type independent. It ensures diversity while reducing the dataset size. It has reasonable computational requests, and it may help in re-annotating wrong labels. This work is still under peer review, so feel free to contact us if you are interested. And thank you for listening.